I want to spend a few minutes this morning reviewing diffraction and interference of waves. Firstly, we're going to look at interference of waves in one dimension. So you got two waves coming towards each other, maybe two waves going in the same direction, but one's going faster than another. They encounter each other. They produce what we call an interference pattern. That is a wave pattern that looks different than either of the individual waves. Now, how do we figure out what that wave pattern looks like? Well, we use something called the superposition principle. And that means just adding up how far above or below the equilibrium position each of the wave is. So let's look at how far above this first wave is. Let's look at how far below the second wave is, and then let's add them together. Now, ideally, we do that at an infinite number of locations. Okay, the best pattern, the best representation of the pattern would be if we looked at an infinite number of places, but we realistically can't do that. So what we're going to do is just analyze on graph paper where the vertical lines are. Okay, the more locations you analyze, the better, but it's sufficient to analyze wherever you have a vertical line. So the first thing we want to do is look at where they overlap. Okay, and that's this area right here. And let's look at where they overlap: position 1, 2, 3, 4, 5, 6, 7, and 8. At position 1, we've got wave A that's 2 blocks above. At position 1, wave B is 1 block below. So we've got 2 above, we've got 1 below. What do those add up to be? 2 plus negative 1 gives me 1. So we're going to put a little X at position 1. We're 1 block above the equilibrium position. All right, position 2, we've got, 1, 2 above, and we've got 2 blocks below. 2 plus negative 2 gives me 0. So the wave position, the resultant interference pattern at that spot would be 0. Next one, position 3, we've got 2 above, and we've got, it looks like you got about 2.5 below. 2 plus negative 2.5 is negative 2.5. So we're going to put a little X at not negative 2.5, negative 0.5. Next one, it's almost 2 above. We're not going to lose too much sleep over the fact that it's just short of 2 above. And this one's going to be 3 below. 2 plus negative 3 gives me, it's not quite negative 1, but it's pretty darn close to negative 1. Remember I said yesterday, it doesn't have to be perfect. Okay? It's a little bit off of negative 1. If we made it negative 1, that's fine. If you make it negative 2, that's wrong. Okay, that's too far off. But if you're real close, then that's good enough. Okay, here we got about 1.5 above, 3 below, negative 1.5-ish. 1.5 above, about 3.5 below. 1.5 plus negative 3.5 gives me negative 2. So we're going to put a little X at negative 2. And we got 2 more positions to look at here. Position 7, 1 above, 3.5 below. 1 plus negative 3.5 is negative 2.5. And then finally, we got about 0.5 blocks above. And then we've got 3.5 blocks below. 0.5 plus negative 3.5 gives me about negative 3. Well, that's where they overlap. Now comes the easy part. Let's just look at the part where they don't overlap now. Just fill in the X's. Literally, let's just fill in the X's right here and right here. There's nothing to add to that where they don't overlap. And now let's just trace it over. So at that moment in time, the wave looks like that. The wave looks like the red line. Not like either of the black lines, but it looks like that single red line. What do we call this? Constructive or destructive interference? This is destructive interference because it's producing a wave that is smaller than the individual waves that make up that resultant wave. All right? Unit test next Monday. You will get one of these, as I said yesterday, on your unit test next Monday, for sure. Yesterday, we also looked at a concept called diffraction, which we related to interference after we did the 2 of those topics. Diffraction was the spreading out of a wave. when a wave goes through an opening or around a barrier, hey, we see that, well, only part of it ends up going through, goes through that opening. But the edges of that wave spread out, and the spreading out of that wave is called diffraction. Now, in this case, the diagram that I've drawn here right now, we've got a little bit of diffraction. The angle of spread is fairly small. But there are ways to affect the amount of diffraction that takes place, to change the angle of spread, to make it bigger or even smaller. The three ways that we can change it, change the amount of diffraction that takes place, is by, one, changing the size of the opening. If I decrease the size of the opening, if I make the opening size smaller, what's going to happen to the amount of diffraction? Am I going to get less diffraction, or am I going to get more diffraction? In other words, is it going to spread out less, going to spread out more? Emma? Yeah, right. You're going to get more diffraction. The amount of diffraction increases. It's going to spread out more. It's going to look like this instead of what it looked like the first time. Good. What about the frequency of the wave? If we decrease the frequency, using the story that I told you yesterday, if we go from FM radio waves, which is megahertz, to AM radio waves, which is kilohertz, if we decrease the frequency, does diffraction decrease or does it increase? It decreases. Sorry, it increases. Right. It's like the story that I told you yesterday. With AM radio waves, I was able to hear my radio show at the bottom of the hill. With FM, I wasn't. So with AM, we know that they diffracted more. Small frequencies, as the frequency decreased, the amount of diffraction increased. And I didn't have a story yesterday to relate wavelength to the whole deal, but we know that wavelength has the exact opposite effect as frequency. So with wavelength, if the wavelength decreased, then we would know that diffraction would decrease. Yeah, because again, the exact opposite effect as frequency. If frequency decreasing the frequency causes diffraction to increase, then it must be that decreasing the wavelength would cause it to decrease. Good? And finally, yesterday when we related the two together, diffraction and interference in the same spot, we showed you this diagram where we had two openings. The wave was coming at this barrier, but there was two openings, two places for the wave to go through. And when it went through, it diffracted in both places. So we got two of these diffraction patterns here, two of these spreading out diffraction patterns. But of course, with two diffraction patterns, at some point, we would find that one diffraction pattern would overlap with the other. So we'd get interference taking place. We'd get constructive interference when it was a crest and a crest, or a trough and a trough. We'd get destructive interference when we had a crest and a trough. If these thick lines represent crests and the thin lines represent troughs, then we would have constructive interference where we have crest and crest. Oops, not there. But we would also have constructive interference where we would have trough and trough. So this was a big crest that was produced. This was a big trough that was produced in a big crest, in a big trough, and so on. You kept filling in all of those spots where we had thick lines meeting thick lines and thin lines meeting thin lines. In other words, crest and crest, trough and trough. Then we saw that we got something that looked like this. A bunch of different lines of constructive interference. You guys remember what other name we applied to those? Antinodal lines. Yeah, these lines of constructive interference were antinodal lines. Antinodal lines represented areas where we had constructive interference. Big waves, big crests, big troughs. Versus destructive interference where we had crest and trough, crest and trough, crest and trough, canceling each other out. Looks something like this. Start joining those lines together, or those points together as well, and seeing patterns. You guys remember what we call those areas of destructive interference? Those are called nodal lines. That's where we have complete destructive interference. That's where we have no wave, calm water, or cancellation of whatever wave it is. If this was sound, picture this as sound going through two openings. Okay, if you were standing right here, what would you hear? If I was standing right here, at this position right here, what would I hear? Sorry? I would hear a loud sound, right? I would hear a loud noise. Okay, if I was standing right here, what would I hear? Quiet. It would be nothing. That makes sense? It's odd to think of that, right? I could be standing right here and I hear a really loud noise. I can be standing right beside it and I would hear nothing. Because right here I hear constructive interference. Right here I would hear destructive interference. Right? All right, today now I want to cover some new stuff as well that is another extension of interference of waves. It's called standing waves. A standing wave is a wave that appears to be standing still. You guys saw in the demonstration that we just did that when I send a wave down a string from one end to another end that is attached to something, that wave will reflect back. And as the waves are reflecting back, they interfere with the waves that are still going down. So waves are going this way at the same time, interfering with each other. Now, most times, and you guys saw this in the demonstration, most times the interference pattern, although not random, it's predictable using the superposition principle, it appears to be more or less random. It's not a recognizable interference pattern. But at certain frequencies that we call the resonant frequencies, when the frequency of the vibration that I'm generating matches the resonant frequency of the string, then we get this neat interference pattern that makes it look like the wave isn't moving. You have waves traveling all the time back and forth, but it appears to make the wave standing still because we've matched the natural or the resonant frequency of the string. The diagram that I have at the bottom here is not a great diagram illustrating what a standing wave looks like. It's the best I could do with Microsoft Word. Okay. In the end, we have a wave something like this. But at the same time, it appears as if the wave is going like this. There was a couple of people at the front of the room when I was doing the demonstration that put their fingers on this. And they put their fingers right here and here at the same time. And it felt like the string was at both positions at the same time. Clearly it wasn't. Clearly this crest was going down to this trough and back and forth, back and forth, back and forth, but it appeared to be in both places at the same time. That was constructive interference. Constructive interference at these spots right here that we call antinodes. But you guys also noticed by putting your finger on it and these spots in between, there was actually destructive interference, complete destructive interference that canceled out the waves. We sent waves down at 30 hertz, 30 waves per second going down and coming back, but yet there was spots in the middle or there was spots along the way where the string wasn't moving at all, destructive interference. And there were spots in between there, like here, where the wave was going up and down 30 times per second, making it appear as if it wasn't moving, as if it was standing still. We're going to spend a few minutes now drawing what the interference patterns look like with these standing waves and then predicting using some mathematics at what frequency it will occur at. So you see 4 different sets of parallel lines right now. These represent the ends of the string. So with the demonstration that I have up here right now, this vertical line would represent this end, and this vertical line would represent this end. The first standing wave that's set up, you guys remember what this looked like, right? We had one antinode. I'm going to draw a dotted line representing the bottom of it. This one you could actually see moving up and down, right? But we only had one antinode. We had a node at both ends, and we had an antinode in the middle. The second one that you saw had 2 antinodes. So it would look something like this. The third one had 3 antinodes. So it would look something like this. And then 4 antinodes, and so on. We don't need to draw anymore. Like the first 3 is good enough. Because you can imagine what they're going to look like, right? 4 antinodes, 5 antinodes, 6 antinodes, 7 antinodes, and so on. Now, pay close attention to this. The length of the string we're going to define as L. Now we want to come up with a relationship between lambda, the wavelength, and the length of the string, right? Lambda is the length of a wave, one complete wave. L is the length of the string, which may happen to be the length of a wave, but not necessarily. I'm going to draw a wave over here. And I want to use that to help us to see how much of a wave that we have in these 3 situations. Okay, so let's look at the first one here. Okay, let's look at the first one. We start right here, and then we trace it to this point right here. Right? Do you guys agree that that's the same as the first wave that I drew? From here to here? How much of a wave is that? How much of one complete wave is that? That's a half a wave. So I'm going to say that L is equal to 1/2 of lambda. That make sense? Okay, let's look at the next one. We're going from here, okay, this position right here, we trace it through, and then we stop right here. How much of a wave is that? That's 1. So we're going to say in this case that L is equal to lambda. Now the next one, we're going to start right here and trace it through. Looks like it goes to there. How much is that? That's 1.5. Now you could say L is equal to 1.5 lambda, but I'm going to use a fraction, and you're going to see why in just a minute here. So I'm going to say L is equal to 3/2 lambda. It's not wrong to say 1.5 lambda, but it's easier to see a relationship that we want to see if we make it 3/2. Now, what I want to do in each of these cases is rearrange the equation that I just derived to solve for lambda. So in this case, lambda becomes 2L. The L goes up by multiplying. This one's easy. If L is equal to lambda, then lambda is equal to L. And this one's a little bit harder. Take the 2 up by multiplying, the 3 down by dividing. Lambda would be equal to 2/3 L. So get L in terms of lambda, but then rearrange it to solve for lambda. Finally, what I want to do is come up with an equation using the universal wave equation. Remember that V equals F times lambda equation, or F is equal to V over lambda? Come up with an equation that describes the frequency at which each of these standing waves will occur. So for this one, we're going to say F is equal to V over lambda, or F is equal to V over 2L. For the next one, we're going to say F is equal to V over lambda, but lambda is L, so we're going to replace it with F is equal to V over L. And finally, for the last one, the third one here, we're going to say F is equal to V over lambda, which is what? V over 2/3 L. That's a little ugly, so I want to simplify that a little bit. When you divide by 2/3, it's the same thing as multiplying by 3/2. So it becomes F is equal to 3V over 2L. Now I want you to see if you can spot a relationship here. The first one, we call this, by the way, the first harmonic. The first one occurs at a frequency of V over 2L. If you take the speed of the wave in that string and divide it by 2 times the length of the string in meters, then the frequency that you get there would be the frequency at which you would see the first standing wave, the first harmonic. The second one, the second harmonic, would occur at the speed of the wave divided by the length of the string. The third one would occur at three times the speed of the wave divided by 2 times the length of the string. Look at the relationship here. V over 2L. V over L is the same as saying 2V over 2L, right? Right? V over L, isn't that the same thing as 2V over 2L? Right? So we got V over 2L, 2V over 2L, and 3V over 2L. If we call this the first harmonic, then the second harmonic is twice the value of the first one, right? Because it's V over 2L and 2V over 2L. And the third harmonic, the first one was V over 2L. This is 3V over 2L. So the third harmonic is 3 times the first harmonic. What do we see in the demonstration a few minutes ago? The first standing wave that we saw occurred at 5 hertz. When did the second one occur? 10 hertz. When did the third one occur? 15 hertz. Fourth one occurred at 20, 25, 30, 35, and so on and so on and so on. So the resonant frequency, the fundamental resonant frequency is V over 2L. But then these supplementary harmonics or supplementary resonant frequencies occur at twice that value and 3 times that value and so on. Now, you're going to do some problems involving this. And the bad news is these equations aren't on your data sheet. The good news is all you really have to be able to derive, we've derived 3 of them on the board here right now. All you really have to be able to do is derive the first one. Why? Well, because the second one is just twice the first one. So if you want to find, let's say, you want to find the third harmonic. The question says, what's the third harmonic? What's the easiest way to do it? Get the first one and then just times the number by 3. Okay? Get the number for the first harmonic, the 5 hertz in our demonstration, and then times it by 3. Okay? Let's do an example here. Okay. This example is unfortunately not in your book, but that's okay. Just one here. It says a 25 centimeter long string is set into vibration. And when we do that, right, let's say it's a guitar string, whatever. We pluck that string and it vibrates at 1 million different frequencies. Maybe not literally 1 million different frequencies, but lots of different frequencies. But most of them die out, like instantly, almost instantly. Most of those frequencies die out. The only ones that stick around are frequencies that correspond to resonant frequencies, the frequencies that will produce standing waves in that string. And that's what we end up hearing, is the resonant frequencies of this string. This string is 25 centimeters long. The speed of the wave is 500 meters per second. We want to know the first three possibilities for harmonics in the string. I'm going to derive an equation once again for the first harmonic. Why? Because this equation isn't on our data sheet. So I'm going to figure it out. I might remember it from the analysis that we just did, but when all is said and done, 2 weeks from today, when you write your final exam, you probably won't remember it. Be able to figure it out. Okay, the length of this string is L. We know that lambda is equal to how many L's? Or sorry, I should say L is equal to how many lambdas? It's a half, right? That's a half a wave. So we would say that lambda is equal to 2L. And we know that F is equal to V over lambda. Therefore, F is equal to V over 2 times L. There's my equation that I just derived. F is equal to V over 2L. That's the first harmonic. Let's not worry about the second and third right now. Let's just worry about the first one. F, the first harmonic, is equal to V over 2L, which is 500 meters per second divided by 2 times 0.25 meters. Got to be in meters here. So 500 divided by 0.5, I think gives us 1,000. Now, what are your options right now for finding the second and third one? Kessler? Yeah, you could derive the equation for the second harmonic and derive the equation for the third harmonic like we did a couple minutes ago. But what's the easiest way, Kessler? Multiply it by 2 and 3. So F1 is 1,000 hertz. F2 is 2 times F1, or 2.0 times 10 to the 3 hertz. And F3 is 3 times F1, which is 3.0 times 10 to the 3 hertz. Does that make sense? I'm going to give you a worksheet in a second. I'm going to ask you to work on questions for the rest of class. Let's say one of those questions on the worksheet, there's quite a few of them. I think a couple questions ask you to do this. Let's say that one of those questions says the frequency of the third harmonic is 1,500 hertz. What's the speed of the wave? You can derive an equation for the third harmonic, right? Or you can say, oh, hey, the frequency of the third harmonic is 1,500 hertz. The frequency of the first is 500 hertz, 1/3 of that. And then use the equation for the first harmonic to get what you're looking for, the speed of the wave or the length of the string. So here's the rule of thumb. You always want to go through the first harmonic. You might need to find the fifth harmonic from the first by multiplying it by 5. Or you might be given the 14th harmonic, then divide by 14 to get the first harmonic. But you always want to be dealing with the first harmonic, because that allows you to not bother deriving the equations for any other harmonic other than the first harmonic here. Does that make sense? Okay, I'm going to give you a worksheet right now. There's 2 sides to that worksheet, and I'd like you to work on the front side of that worksheet, the front side only of that worksheet.